Okay, so nothing. I was just saying that the connection between the physics and the metaphysics of time has proven to be a fruitful area, and that there has been quite a bit of connection related to issues regarding simultaneity and special relativity, and possibly general relativity. And then I was mentioning that there have been attempts, such as that of Monson, that try to even connect these issues to quantum gravity. And in particular, his work focuses on things like loop quantum gravity and geometrodynamics. And then there is a rather convincing story by Chris Wuthrich that says that this is actually not really a way to recover presentism, even if one appeals to quantum gravity in this way, at least to these specific versions of quantum gravity. Now, what we want to do today is basically to look at what might seem prima facie like a friendlier environment for this kind of project. And so the environment that we have in mind is this kind of non-relativistic theories of quantum gravity, which are theories that rely on this specific kind of geometry, which is torsional Newton-Cartan geometry, TNC for short. And the idea is that since we are dealing with a non-relativistic space-time, we should be able to actually recover quite a bit of the structure that the A theorist wants to recover. And then we can transform basically the debate between the A theorist and the B theorist in something close to a naturalized, empirically accessible question regarding what is the correct theory of quantum gravity that we want to use. So here I have just some examples of possible theories of quantum gravity that rely on this non-relativistic kind of geometry. So we have non-relativistic string theories, we have Raval-Lifshitz gravity, which is a perturbatively renormalizable theory that can be applied to certain cosmological construction, and then we have a non-relativistic version of the ADS-CFT correspondence. So these are some of the examples of theories that might do the job for the A theorist. But now, after having told you that this might be a friendlier environment, I actually want to tell you the real goal of the talk, which is to say that this is not really a friendlier environment. So really, as we're going to see hopefully by the end, there is not really a better situation in terms of how to make sense of simultaneity in these theories than there is in things like special relativity and related theories. So basically, what we want to start with now is to define what it means to have a standard of simultaneity. So the first half of the talk will be devoted to actually presenting a reasonably precise criterion as to what it means to be simultaneous for a theory of physics to display absolute simultaneity. And then after we've done that, we'll check our criterion with the specific theories. So the first requirement actually that we want on any reasonable criterion of this kind is that it has to be expressed in something like differential geometry and related kind of fields so that we can actually compare it with the structure of TNC geometries. Now we just take as meaning for simultaneity simply purely spatial separation and absence of temporal separation. Now this should be reasonably intuitive as to what we take simultaneity to be. And we will take basically a standard of simultaneity to be something along these lines. So that given a single event, all other events can be divided based on objective coordinate-dependent features of the structure of space-time into those that are spatially separated from that event, which we count as simultaneous, and those that are not. So the first thing that we need to ask ourselves and to answer is what we wish to count as space-time structure. So what we want to, the account that we want to use, the account that we want to use of space-time structure in this talk is going to be basically a variant of the functionalist approach to space-time that has been popularized by Knox. Now, I should mention that it's not strictly necessary for what we're going to discuss later. Really, the only assumption that is required is that you identify space-time with the metric, but it's nice to have a more precise description of what is going on here so that we can make some more precise claims. So basically, we follow Knox and we take space-time structure to be whatever components of our theory determines the inertial structure. So in particular, basically what counts as an inertial frame of reference. Now in classical general relativity, the metric field is space-time because it is the metric field that tells us locally what we should count as a local frame, as a frame of reference, and what does not count as an inertial frame of reference. And so this is what we take as our definition of space-time, which in all our examples will be the metric, as I was telling you before. Now, is simply providing the inertial structure of space-time enough to tell you whether or not your space-time admits of a standard of absolute simultaneity? Now, the answer to this question seems to be no. And the answer to this question seems to be no for a simple fact that Minkowski space-time presumably does not admit a standard of simultaneity, but Galilean space-time presumably does. And the inertial structure in them, in and of itself, we need a way to distinguish what is different in their inertial structures so that we can know why Galilean space-time counts as having absolute simultaneity and Minkowski space-time does not. So the first approximation to a criterion that I'm going to propose today is this Sim1 condition. So Sim1 basically tells us that a space-time admits a standard of simultaneity if and only if its inertial structure is given in terms of two independent components for space and time, or equivalently, if its group of space-time symmetries has distinct generators for space and time translations. So this is basically developed to make sense of the difference between Minkowski and Galilean space-time, because in Minkowski space-time, the Poincare transformations mix space and time, as we are familiar for special relativity. So we cannot really distinguish a space translation from a time translation for the simple fact that then we can apply a Lorentz transformation and mix them together. So we cannot define a notion of purely spatial separation in Minkowski that is independent of a choice of reference frame. Now, this is not true in Galilean space-time, because Galilean space-time is basically defined as that space-time whose space-time symmetry group is the Galilean group, and the Galilean group has a different set of generators for space translation and time translations. So we can actually have a coordinate independent definition of purely spatial translation in Galilean space-time, which is not something that we do not have in Minkowski space-time. Now, again, is this enough? Well, it is enough as long as we can basically take a local reference frame, which is a reference frame that we define just as a point, and extend it to a global reference frame. Now, we can do this whenever our group of space-time symmetries acts as a global symmetry group for our theory. This is the case, for example, in special relativity. This is not the case if you're dealing with general relativity. Equivalently, when we're dealing with curvature, which is the difference between general and special relativity for our purposes, then we cannot do any more this trick of simply taking a local reference frame and just extending over all of space-time this separation that we've defined, but we need to be more careful about what we are doing. Otherwise, we're not going to get a reference frame over all of space-time, because curvature is just going to basically destroy our reference frame. So does this mean that we cannot actually define a standard of simultaneity as soon as we have curvature? This seems to be too quick, and the reason why this seems to be too quick is that while local frames do not extend to global ones, this does not seem to be what we really need for the account to go through. What we actually need is a story as to explain how we can connect the local reference frames at different space-time points so that we can get something like a spatial hypersurface out of this thing. And we do this in general relativity again, using basically the Levi-Civita connection and tangent bundle, which basically moves around our local reference frame around space-time and tells us how to glue different choices of local inertial frames. So basically, through the Levi-Civita connection, we define standard of parallel transport so that when we move vectors around in space-time, the connection tells us which vectors count as parallel to which. And we call this the affine structure. Now, through the affine structure, we can get away with only using local inertial frames because, again, in this very picturesque way, what we can do is that we can define a local reference frame at a point, define what counts as space and what counts in time, and simply bring it around space-time using the connection. Now, of course, in general relativity, we're not going to have an objective split in this way of space and time, but at least we have a story now as to how we can, even in the absence of a global reference frame, still define a notion of a standard of simultaneity. And we can ask ourselves, once we know locally what is simultaneous with what, how we can extend this to something that makes sense for the entire space-time. Now, two very short points as to the relation between the affine structure and simultaneity, so that we can now get very quickly to the second condition that we want to impose. So if the affine structure is to play the role that we want it to play, it must be the case that this connection is fixed by the metric, so that it's fixed by inertial structure, which is the case, for example, in general relativity. So the Levi-Civita connection is fixed by the metric. Why do we ask this? We ask this because, as we have said, the metric defines what we mean by space-time in this context. The inertial structure tells us what space-time is. And now, if we do not have this condition, now we find ourselves in the somewhat unfortunate situation that what we count as simultaneous with what, so our notion of simultaneity, is in some sense independent of space-time. It's something over and above space-time itself, because we need to specify something beyond space-time, which is the affine structure, which is not fixed by the space-time structure, by the inertial structure, to make sense of what counts as simultaneous with what. Now, in this situation, if you want to use this to construct an actual metaphysics of time, this seems like a somewhat a very unfortunate situation, because we have to count the basic feature of our metaphysics of space-time, which we define as absolute simultaneity here, basically as non-spatiotemporal. Now, you might be able to work this out, but this seems to push you in a very bad spot if you want to make sense of this notion. Now, the other point that I should mention is that the connection should basically be compatible with the split that we define for Sim1. So for Sim1, if you remember, we have said that we can basically divide whatever is going on in our space-time into spatial translation and time translations, or we can basically divide reference frame into a spatial component and a temporal component in an objective way. Now, we do not want to lose this property once we use our connection to move our reference frame around in space-time. So basically, what we want to do is that we do not simply want our reference frame to be splittable in this way, but we also want our connection to split basically in a component that tells us how to move in time and a component that tells us how to move in space. So that now we can actually define, given a local split between space and time, how this extends to a notion of simultaneity, which in this case, again, means just purely spatial separation and no temporal separation. So again, the connection simply should be decomposable in two components, one for space and one for time, which means that it should be compatible with Sim1. So now we get to Sim2, which is the second condition that we ask for a notion of simultaneity. So a space-time admits a standard of simultaneity if and only if its inertial structure fixes its affine structure, first clause, and does so in a way compatible with Sim1, which is the second clause. And it simply means that by specifying two independent components of the connection, there is one associated with space and one associated with time, so that we can make sense of this notion of purely spatial separation and purely temporal separation. So now we simply put together the two conditions. So Sim1, in the absence of curvature, tells us what is spatial separation and what is simultaneous with what. In the presence of curvature, we also add Sim2 to our definition of simultaneity, and we need to actually define locally split between space and time using Sim1, and then extend it to a notion of purely spatial separation and purely temporal separation through the use of the affine structure whose properties are encoded by Sim2. So this is basically going to be our working definition of what it means for a theory to have a standard of absolute simultaneity. So if a theory behaves like this, then we say that it has a standard of simultaneity. If it does not, then it does not. As you see, Minkowski, as we said, Minkowski spacetime and special relativity do not satisfy Sim1, so they're not going to fall into that category. General relativity does too, plus general relativity, the connection in general relativity does not satisfy Sim2, in that while it is fixed by the inertial structure, it does not split in a space and time component. Now we want to compare this with the structure of torsional Newton-Cartan geometries, which, as we have said, is the basic geometric language in which we express these non-relativistic theories of quantum gravity that we have said the A theorists might be interested in order to make sense of their metaphysics in a way that is compatible with physics. It is naturalistically acceptable. So we want to look at Sim in the context of TNC, and we want to check that TNC satisfies both conditions of Sim that we have defined. Now, if TNC does not satisfy one of these conditions, then we are going to say that there is no standard of simultaneity there, and so that the theories are not really amenable to the type of treatment that someone who needs a standard of absolute simultaneity to make sense of their metaphysics wants to give to them. And in particular, as we are going to see, it is going to be the torsion that is going to play a quite important role in this story. So let's start from some basic facts about torsional Newton-Cartan geometries. So basically, these are non-relativistic geometries where the local space-time symmetries are given by the Galilean group, not by the Poincaré group, as you do in general relativity. And the Galilean group has 4 generators, as I was telling you before. So we have a generator of time translation, a generator of space translation, a generator of Galilean boost, and a generator of spatial rotation. Now, if these were Minkowski space-time, we would simply collapse the first 2 and the second 2 together, and we would have a generator of space-time translation and a generator of Lorentz boost. So as you see, we have basically a split into a spatial and temporal component for the generators of the Galilean group. Now, the fundamental geometric objects that we define for this theory are this non-vanishing one-form T mu, which is simply connected to H. So it is connected to time translations, and we call this the clock form. And then we have this symmetric rank 2 tensor H mu nu, which is associated with the space translations, so with PA, which gives us basically the spatial metric of our theory. And then we simply define a Galilean space-time as a triple. Now, this is a vacuum space-time. We're not defining any kind of matter here. As a triple given by a generic d-dimensional manifold, our spatial metric, and our clock form, which, again, gives us what we wanted, which means that H mu nu and T mu are the analogs of the metric G mu nu in general relativity. Now, what is the status here of Sim? Now, Sim1 seems to be straightforwardly satisfied for what I was telling you before. It is straightforwardly satisfied because we have a generator associated with time translation and a generator associated with space translations. And so we can actually split in an objective coordinate independent way what counts as space and what counts as time, at least locally. Now, the real problem, as we are going to see, is with Sim2, because there we need to look at the relationship between the inertial and the affine structure in TNC. And as we are going to see, the peculiar feature of these TNC geometries, which is torsion, is basically going to imply that we cannot actually define the affine structure in terms of the inertial structure. So we depart from the analogy with general relativity here. And so that we do not really have a notion of simultaneity that satisfies Sim2. So the problem comes from Sim2 in this case. So let me just, how much time do we have, Sam? Okay. Okay, yes, that's fine. So let me start by basically saying a couple of things about torsion. So when we are given basically a connection or an affine structure, we can decompose this into 2 components, a curvature and a torsion. And in the absence of torsion, of course, the curvature is always fixed by a metric. Now, in general relativity, when we take the Levi-Civita connection, we can use a notion, a condition that is called metric compatibility, which tells us basically that the only connections that are acceptable in general relativity are torsion-free connections. So we cannot have any torsion. Actually, torsion enters into general relativity only if you want to try to describe fermions. If you want to describe fermions, then you have to throw in some torsion there. But in just standard general relativity, you do not care about torsion, and you actually have to use torsion-free connections. Now, in torsional Newton-Cartan geometry, the story is a bit different. So we define 2 different torsions, as usual. So we have one associated with time translations, so with the clock form, and we have, which is equation 1. And then we have one associated with spatial translations, which is equation 2. And we can make disappear the spatial torsion via a condition that is analogous to metric compatibility in general relativity. Now, what we cannot make disappear in general is the temporal torsion. So the fact that is going to be important for us is basically going to be the fact that the T mu nu 0 that appears in equation 1 on the right side of equation 1 is sometimes going to be different from 0. So we cannot basically express it in terms of the basic geometric objects in terms of which we are defining our theory, so the T mu and H mu nu variables. So in general, we cannot express the affine structure in terms of these objects, and we cannot then express the affine structure in terms of the inertial structure when we are dealing with torsional Newton-Cartan geometry. And here we have a very quick classification of the kinds of Newton-Cartan geometries that you can have in terms of the temporal torsion profiles. So you can have a torsionless case, which is the good one, the one where torsion does disappear at the end of the day. And so we are fine with that. Then we have a twistless torsional profile, and then we have an arbitrary torsion profile. Now, in the second two cases, in both of them, we have a non-zero torsion, and so we cannot express the affine structure in terms of the inertial structure, and so we cannot fix the connection in terms of the metric and of the space-time structure, which means that Sim2, as we are defining it, is violated, which again means effectively that if we were to try to define simultaneity here in the way that we've described, which seems to be a reasonable geometric approximation to what simultaneity should be in one of these theories, then we are faced with the somewhat unfortunate conclusion that simultaneity is not a property of space-time. It is not a spatiotemporal property, which kind of looks like a contradiction if one is trying to do the metaphysics of time of these things. Now we can try to see this a bit more quickly by means of a simple example. So we can take the proper time between 2 points A and B in the manifold. We take a curve between them, and we define this integral here that basically tells us how much time has passed if you were an observer moving along the curve gamma. Now, you can prove that already in the case of twistless torsional Newton-Cartan geometry, as soon as the temporal torsion is different from 0, then it turns out that T gamma depends on gamma. So you have a path dependence of proper time, which, if you're familiar with that, is basically what happens in the Twins paradox in special relativity. Depending which path you take to connect 2 points in space-time, you get basically the different amount of proper time as expired. So this seems to be a prototypical relativistic effect that we have just recovered in a non-relativistic theories. There is no Minkowskian geometry here, there is no Poincaré symmetry here, but just we have thrown in some temporal torsion, and already we have a phenomenon of this kind. So in other words, proper time depends on the path that you choose between A and B. And so at the end of this path, we're going to get different inertial frames at B. So the conclusion here is that if we have a non-trivial torsion profile, such as this one, then the parallel transport of an inertial frame along gamma is going to depend, on the path that we choose, and it is basically not going to be determined by the inertial structure. We're going to need the full power of the affine structure, which cannot be defined in terms of the metric, which means basically that in the presence of non-zero torsion, we cannot simply rely on either spatial or temporal translations, and that's it, in order to specify which relations obtain between two locally defined frames of reference, which again, basically means, if the argument is clear enough, that if we just define simultaneity as spatial separation and lack of temporal separation, then we cannot simply deal in this context where we have torsion, we cannot simply use the tools that we have defined to say what it means to have spatial separation or temporal separation, to simply say what is simultaneous with what. We cannot really define what it means to be purely spatially separated or purely temporally separated. Once we have torsion, we have to also take into account the torsion into this description. Now, there is an equivalent version that was suggested, I think, yes, that was suggested to us by Wetherall of this argument that is roughly equivalent to this, where it's a bit more mathematically involved, but it's slightly more intuitive in terms of the geometric picture that comes out of that, in the sense that as soon as you have this non-zero, as soon as you have the, okay, I'll close it up. As soon as you have this non-zero torsion, then this means that concretely it means that this clock form is something that you call a non-closed, is not a closed form. It doesn't count as a closed form. Now, we don't care what it means. What we care about is that if the clock form is not closed, this means that you cannot define basically an hypersurface of simultaneity into the space-time. You can check Malaman's book on general relativity and Newton-Cartan geometry for the proof that a non-closed form implies lack of a surface of simultaneity. So this is, again, an equivalent version of this argument. It's a bit less mathematically clear, but it should be a bit more intuitive geometrically. Now, just to conclude very briefly, now let us very briefly discuss as to how one might try to avoid the conclusions that we're trying to give, so that symmetry is violated, and thus one cannot define what it means to be simultaneous in these geometries. So the most obvious option is that you should give a definition of space-time that does not rely on inertial structure and incorporates the torsion tensor. Now, as I was saying before, what it seems to be going on here is not really that the definition of inertial structure that we give is crucial for the whole argument. What really matters is simply that one is willing to say that there is no more space-time structure than what is defined in terms of the metric, which seems eminently plausible, given most views, I think, on what space-time is. And it seems to be guaranteed by most approaches to what a theory of space-time should be. Moreover, it is somewhat unclear how to interpret torsion, at least it is unclear to me, let's say, how to interpret the torsion tensor as a space-time quantity, partly because I cannot define it in terms of the metric, so I have no idea how to define a field that I can reasonably associate with space-time and which incorporates torsion. And furthermore, it seems that the torsion tensor is indeed introduced in most cases to basically accommodate for peculiar types of matter. So in GR, it is fermions, and even in these TNC theories, it is basically, we need to move to the torsional versions of the theory because of some peculiar configurations of matter in our theory. So it is somewhat unclear to give a straightforward geometric understanding of the torsion tensor. Now, when we talk about curvature, we have an understanding like this. It is simply the geometric structure of space-time. And we do not need to rely on its action on reference frame. You can give an intrinsic definition in terms of things like the Riemann tensor, and we can associate the Riemann tensor to certain properties of space-time. It seems in this case that you just have a torsion, and the only reasonable physical interpretation that we can give of this torsion is in terms of its action on certain inertial frames. We cannot really give a story as to how this action connects to the underlying geometry of whatever space-time is supposed to be. Now, of course, none of this is technically surmountable, in that the A-theorists might be willing to actually go to very great lengths to make sure that these non-relativistic theories of quantum gravity do actually give them a metaphysics of time that is compatible with quantum gravity. And so they might wish to actually provide this definition. There is no a priori reason as to why this should be impossible. It just seems that the task itself is extremely daunting. It's something that it's not exactly reasonable to expect that it's going to be done, though it would be interesting to see someone try, I guess. So now just to conclude, am I on time, Sam? Great. So just to conclude very briefly, so we have seen how some construction in what we have called non-relativistic quantum gravity might be prima facie seem to be more hospitable to the metaphysical desires of the A-theorists, at least of those A-theorists that want to have a notion of absolute simultaneity in terms of which to give their basic metaphysical constructions. And we have seen that these theories actually do not provide an absolute standard of simultaneity, at least as we have defined an absolute standard of simultaneity in this reasonably, hopefully precise way. And so again, the crucial issue in defining absolute simultaneity here is that the relevant geometries have temporal torsion, and so you cannot define the affine structure in terms of the inertial structure, or you cannot define a connection in terms of the metric, or you cannot define, if you want, simultaneity in terms of space-time properties. So while this is somewhat different from what is going on in special relativity, since we do have a clean splitting between space and time, we do not have issues with mixing space and time coordinates. It seems that in the end result and the issues are kind of the same, in that in both cases, we basically end up with some path dependence of proper time, and thus with the fact that we cannot basically define nothing that resembles an hypersurface of simultaneity, not even in these cases. And that's it. Thanks.
Hi, thanks for that. So I suppose, I mean, yeah, to some extent, I think the the aim of digging out some way of getting a privileged foliation in the absence of some kind of new information at this point is one that people after a dynamic view of time should be very wary of. Like, we can come up with different geometries, but we're going to run into the same problems. I suppose I was wondering if you could say something about proper time, because you sort of mentioned that we have this problem that we run into the twins paradox. But of course, I know that there are some people of the view that it's no paradox at all. It's just a question of having journeys that are different lengths. So what one needs for a dynamic view is for there to be change over time. Proper time gives you some time over which there is change, but the twins paradox tells you that it happens differently on different parts. But so to what extent do you think that what you've shown is a problem for kind of a theory, or merely for a particular way of conceiving simultaneity, where that's the state? I suppose that's the question. Sorry, it's a bit confused.
No, it's fine. I mean, so let me try to rephrase that. So basically, the question would be, if this is a problem for any kind of possible kind of A theory, or just a problem for a kind of A theory that in some sense wants to appeal to some notion of simultaneity, right? Okay. Now, if that is the question, if you're capable of constructing a kind of A theory that is completely independent of any notion of simultaneity, and so is able to deal with these kind of issues, and so you don't really care about basically connecting what is going on at different, you just want to define basically. So maybe I can try to, so the quick answer is yes, it applies only to the simultaneity case. Now, the issue that I would see there, of course, is that basically what you're trying to do is basically that you're trying to define some kind of A theory only in terms of what we're calling here sim1, right? You just want to have a split between space and time so that you can say that this is my spatial component, this is my temporal component, and the spatial component evolves along the temporal component. But I don't really care about basically having some kind of story that applies to the whole of space-time. It just needs to apply to a single geodesic, right? A single curve in space-time. Now that, I guess, is fine. In principle, it's fine. The main problem that I would guess you could run into that is that you would have the issue, as you do have then when you move to this proper time thing, that the two observers cannot agree as to what is simultaneous with what. And then you need to have like a very good story as to how, I guess that there are versions of the A theory where you can actually give a reasonably consistent story as to how their judgments are supposed to go together. But you need to give a very precise story as to how these judgments are supposed to go together. And presumably, if you at least want to apply to these TNC geometries, now you need to do this. So basically, the point was this, that you do get something that is very close to the twins paradox in that you have basically path dependence of proper time. And so that is similar to general relativity, but the way that you get there is very different. So what I would worry immediately is that any story that tells me how the A and B basically, gamma and gamma prime, let's say, are to interact between themselves and to basically exchange information, that story might actually run into some problems due to the fact that there is torsion here. It's not merely a matter of the fact that we are not splitting cleanly space and time, but we have this torsion tensor that, I mean, I should actually think about it a bit more as to how exactly it might create a problem. I would suspect that it might create some different issues than the ones that you run into when you have the normal twins paradox, let's say, in special relativity.
So I'm a little bit confused about something early on near your starting point. You want to use parallel transport of the affine structure to compare reference frames at different points. But even in an ordinary Riemannian manifold with no torsion, parallel transport depends on the path that you transport. So doesn't that already fail even in the absence of torsion?
So yeah, this is a slight difference that I was not mentioning between basically Riemannian geometry and this Newton-Cartan geometries. So in the Newton-Cartan case, absent torsion, you have path independence of things like proper time and everything. So basically you can actually define, for example, an hypersurface of simultaneity and just translate it forward, and you don't have issues of that kind. It is path independent. As soon as you have torsion in the Newton-Cartan case, then you have these issues. In the Riemannian geometry, you're right that you don't have path independence of this kind already. So you cannot, so these two notions do not work in Riemannian geometry. That is true. But in the absence of torsion, I'm reasonably sure that they work in the case of Newton-Cartan geometry, because you don't have this path dependence in that case. Yeah.
Very quickly, can you please justify, I mean, make it more explicit why you think that the Newton-Cartan case is important? Why did you start with that rather than, you know,
directly with Riemannian geometry? So the idea was exactly that in the case of general relativity, let's say, we kind of already have a reasonable idea as to why these ideas cannot work. But we do actually have proposals for what quantum gravity might be like that are based on these Newton-Cartan geometries, and they're not based. The idea is that the fundamental level, if this worked exactly, you would have a quantum gravity theory, which is based on this Newton-Cartan geometry, and then you can use that quantum gravity theory at the fundamental level to justify the fact that you have some kind of absolute simultaneity standard, and then you need to give an emergent story as to how you recover differential geometry.
I don't know anything about this torsional Newton-Cartan, so this is just a question to say a little more. So is the kind of point that, you know, if I had like a Cauchy surface with a bunch of ideal clocks, I synchronize them all, and then let them go, you know, now like they're all programmed, like after a minute, they all stop, and now I draw that surface won't necessarily be all space-like anymore.
Basically, yes. Okay. Yes, you cannot really, once you have path dependence of this kind, you cannot really draw anything that resembles a space-like hypersurface of that kind. I mean, you can draw it, but you're going to destroy it immediately, as you said.
Yeah, very nice. Thanks, it was very cool. During your talk, you distinguished between inertial structure and the affine structure. But for me, the two of them are like pretty much related. Or like the inertial structure is something like what a free particle would follow. And in Newtonian theory, that's a straight line. In general relativity, it's a geodesic. And basically, it's the affine structure, which is defining what is geodesic or what is your straight line. So for me, both of them are really tied together. So how are you defining inertial structure? By means of...
the question would be, what's the difference between the inertial and affine structure, right?
Yeah, basically.
Okay. So the affine structure, so the idea here is that the inertial structure is basically the structure of local reference frame that you can find in theory. So whatever, for example, the metric tells you that locally the metric is going to look like Minkowski spacetime in general relativity, right? And we define this structure basically of, a clean way to see this is maybe through something like a tetrad. So the inertial structure is given by the 4 vectors at each point, and then the connection is the affine structure. Now, in normal general relativity, the connection is fixed in terms of the metric, but in these strange cases, it is not. But the idea is that, like, here, at least by inertial structure, we mean the local structure of reference frame that you can define for the theory, which is given by the metric. And by affine structure, we basically mean the connection, which tells you how to connect different points in the manifold, or how to move from one set to the other.
But then your notion of inertial structure doesn't have anything to do with what a free body would do, or is it?
No, I don't
think.
Vectors
in any point of space-time.
Yes, I don't think so. It has more to do with the local structure of space-time, as we are understanding it here.
Okay, thanks.
Yeah, I had a question about this torsion Newton-Cartan picture. I'm surprised to find out that it's path dependent in the way that you described, because you've got the split between like the manifold, you know, you don't have a single mixed metric. You've got this initial split between the two metrics. So how could, I mean, this is probably just my mathematical understanding, not following through here, but how can it be path dependent and preserve that initial split between the spatial and temporal manifolds? Or maybe another way of putting it is that how can it still be fixed under the Galilei group if it's path dependent in the way that you describe?
Okay. Okay, yes. Basically, this is due to the fact that you're doing this through the torsion. So locally, you still have a Galilean space-time, so you still have the split between spatial and temporal. What is going on here is that you basically have a temporal translation for, let's say, just purely temporal translation. But since the torsions are different between the two curves that you're following, then you're going to end up with basically two different inertial frames. Now, those two different inertial frames that you're going to have in B are going to be related by a Galilean transformation. The idea is that you should still have locally the same notion, but if you count something like a proper time, then that is going to be different. Like locally, the space-time looks the same because locally you don't see this torsion thing. But as soon as you try to connect two different points, you're going to see these deviations and these path dependencies, basically. That should be the story.
Yes, thanks for that. I really enjoyed the talk. I'm not sure if I understood like 90% of it. I might have a naive question here, but it seems to me that the time that you talk about early in your talk has a slightly different meaning than the other two types of time I think that you bring out later on. Proper time and coordinate time are these metric things, right? But for the A theory people, the important idea of is present time, not coordinate time or proper time. And that is, I don't know if that has that might be a pre-metric or non-metric concept. So I'm not sure if we can fully deduce that. Well, as you say, it's a daunting task to come up with a metric explanation of present time. So I don't know if you...
No, I see. I mean, but so on that, you kind of run either on one of two issues, right? So you either have to say that whatever this geometric understanding of time has no analog in whatever the physical theory that we're dealing with is, and then we basically lose any kind of naturalistic grounding for the metaphysics that we're trying to do. So we can, for example, in special relativity, you can just pick up a certain inertial frame and say, this is a special one and the present is defined in terms of it. Now, the problem with doing something like that is that we have no reason from the physical theory that we're studying to actually pick that reference frame as the correct one. So we end up with issues of underdetermination, and we end up with issues of basically a physically completely unmotivated metaphysics, which one can just say that they're not a naturalist, then it's fine, but then presumably you do not even need to go through all this effort to find a physical underpinning for what you're trying to do. You simply say that you choose a foliation and that is the correct one. Now, as you are correctly mentioning, now, if you want to avoid this thing, then you need to basically choose basically need to find some kind of grounding for whatever you're doing in the geometry that you're studying. And now the issue becomes that you basically need to find, it is true that strictly speaking, they do not need to be the same thing, the time that the A theorist has in mind and the proper time or the kind of coordinates that you define on a manifold. But now the issue is that you need to give a story as to how the time that the A theorist has in mind is connected to those kinds of time, and in a sense in which way they are, if not the same, at least very close cousins, I guess, because they cannot really be too separate. Otherwise, either one emerges from the other, and then you kind of run into the same issues that the real time is presumably what's going on in the physics, and then you don't really need the A-theorist conception. So that was kind of the step that was going on here. There is a dilemma. We want to be naturalists, so we choose the naturalist route. And then once we are there, we basically want to find a notion of time in the physics that is close enough to the notion of time that we want to have in our metaphysics that we can say, okay, that is the time that I had in mind.